Now, the most widely used probability distribution function is the normal distribution. It's also called the Gaussian distribution, after the astronomer and mathematician Gauss. It's also called the bell curve, and it looks like this. So it goes low, high, and low again. And it has this equation. So this is the probability density here. And it's basically exponential, so it's e to the minus x squared over some constant. So as x gets bigger, it's e to the minus a bigger number squared, so it drops away on both sides, explaining the shape. Now in the equation, this mu over here is the mean. That shifts the curve one way or the other. So this particular graph here has the mean of 0. But if you had the mean of 1, it means the curve would go up, peak at 1, and then come down. Sigma here is the standard deviation, or the width of the distribution. That's telling you how fast it drops away. So this graph is sigma of 1, so it drops away quite severely by 1. If you made sigma 10, then the graph would be much lower but go much further out. If sigma was 0.0001, it would be a much narrower distribution. This curve basically tells you that the most likely value, the highest probability density, is near the mean, and it goes down as you go further away. By the time you're 2 or 3 sigma, 2 or 3 standard deviations away, the probability is very low, but it never goes to 0. Not quite 0 even out here. It's very, very close, but there is a extremely small but not 0 probability that you can get values way out here in the wings. Now, why is this distribution so popular? Well, basically, its popularity comes from the central limit theorem. What does this theorem say? Well, basically it says that if you have a lot of random things going on, and you add all their results together, and each of them is independent of the others, so whether one is high or low is uncorrelated with the others, then you get the normal distribution. So for example, let's say you roll 1,000,000 dice. Each dice is random. But if you add up the values of them, you'll get a distribution that looks like this. Or you flip 1,000,000 coins. So if 1,000,000 coins, let's say you count a head as 1 and tails as 0. So you'd expect an average score of 500,000, and then it would drop off in some direction. Let's say, for example, we took every woman student at ANU and we measured the length of their index finger. Now, the length of your index finger depends on many genes, not just one gene, and so the distribution will look something like this, a normal distribution, because there are many genes, each of which has a small effect and which are uncorrelated with each other. So most people will have the average finger length, but some will have it longer and some will have it shorter. So this does actually work some of the time, but it doesn't work actually all that often, because the conditions, vast numbers of random things going on, none of which dominate by themselves and all uncorrelated, are not actually all that commonly met. Most of the statistics we're going to talk about assumes the central limit theorem applies and assumes that this graph, the normal curve, applies, but be careful. In the real world, things are not that simple.